So in a previous lesson, we talked about how ideas from physics influenced some of the modern financial models, such as the Black-Scholes model. We also spoke about problematic sides of the Black-Scholes model, such as ignorance of risk in options due to the insistence of continuous rehedging. Now, in a previous lesson and also in the previous course, we made a point that this approach is problematic at a conceptual level rather than just empirically or numerically. Ignorance of risk of mishedging in pricing options leads to a conclusion that options are redundant instruments. And if this were true, neither market makers nor option speculators would exist in the marketplace, and hence options themselves would not exist either as a result, because there would be no one to trade them. In 2003, Bates surveyed an empirical literature on option markets. He concluded that the risk-neutral methods of option pricing that extend the Black-Scholes model cannot fully capture and let alone explain the empirical properties of option prices. He said the following: to obliteratively attribute divergences between objective and risk-neutral probability measures to the free risk premium parameters within an affine model is to abdicate one's responsibilities as a financial economist. A renewed focus on the explicit financial intermediation of the underlying risk by option pricing market makers is needed. Now, if you're familiar with the financial theory, you would understand what he means by the objective and risk-neutral probability measures. But if you're not, in essence, risk-neutral valuation methods amount to a statement that all prices can be computed as discounted expectations of future cash flows, computed under a very special probability measure Q called a pricing measure or a risk-neutral measure. In this measure, all securities have the same expected returns which are equal to a risk-free interest rate. Dynamics under the physical measure P and pricing measure Q are assumed to be of the same form, while parameters such as drift are related via a free parameter called the market price of risk. I will talk a bit more about the pricing measure Q below, but here I would like to talk about how it reminds me a famous quote of Richard Feynman. He once said that the procedure of renormalization in quantum field theory reminds him brushing garbage under a carpet instead of taking it out. So let me explain what he meant by that. In quantum field theory, if you follow rules of an original model construction and try to compute some physical quantities, you would normally naively get an infinite number. And this happens because you have to integrate over some virtual processes of particle creation and annihilation over very small distances. And this produces divergences in integrals that express these observables. This on its own means that the quantum field theory is only approximately correct and should be replaced by string theory or something else at ultra-short distances. But quantum field theory instead uses a procedure called renormalization that achieves finiteness by adding so-called counter terms, which are assumed to have the same functional form as the original terms in the model. They are then added with coefficients that ensure cancellations of divergences. Now, this sounds very similar to a transition between the physical measure P and pricing measure Q in the financial theory. In both cases, inconsistency of the model with the data is a kind of explained away by insistence that the unseen things should be structurally the same as the things that we see. In the field theory, the unseen is the physics at ultra small scales. In finance, the unseen is the pricing measure as it doesn't exist in any well-defined sense beyond very restrictive assumptions of classical finance, which we will discuss in our next video. Okay, now let's move back from physics to finance and more specifically to option trading and risk of this business. Now, there exist multiple origins of risk in options. One of them is play of demand forces in the option market itself. In a very interesting paper from 2007 called Demand-Based Option Pricing, Garliano, Pedersen, and Patishman looked at it from the modeling perspective. They looked at the problem of option pricing from the point of view of an option market maker, that is an option dealer. Option prices then become functions of demand pressure in the market. In other words, the prices should be such that dealers that maximize their utility to supply precisely the quantities of options that the end users of options demand. Now, these authors found that the marginal increase in the demand pressure in an option increases its price by an amount proportional to the variance of the unhedgeable part of the option. And this sounds very similar to the net effect of risk in the model that we considered in the previous course. This model that I called QLBS model as a short name for Q-learning for the Black-Scholes problem deals with a discrete time hedging for an option. And as we discussed in this previous course, rewinding back the continuous time limit of the original Black-Scholes model is the simplest possible way to remove the assumption of a perfect hedge made in the original Black-Scholes model. And the net result of such unwinding is that the option price receives a risk premium that to the first degree is proportional to a sum of variances of the hedge portfolio across hedge times. This is a similar effect to one obtained by Garliano and co-authors. Now, the topic of this lesson is to talk about other origins of risk in option pricing and trading, as well as to talk about interconnections between the option and stock markets. Let's start with a diagram that we discussed many times in this specialization, namely a diagram that shows the interaction of an agent with the environment. Reinforcement learning solves this task of a sequential decision-making that has to optimize some goals expressed via a cumulative reward function. We called such tasks action tasks and said that they involve a perception task as an intermediate step, because optimizing for the goal now involves planning and forecasting into the future. So the agent observes states ST of the environment and then performs an action AT. As a result, the agent gets a reward RT while the system moves to a new state as T plus 1. Now, in a general setting of reinforcement learning, probabilities of transitions to new states, ST plus 1, may depend on the action AT taken by the agent. This is called the feedback loop. It means that actions of the agent may impact the future, but of course they do not have to. Models where actions of an agent do not impact the future can simply be viewed as a special case of models where such impact is present. Now we can view option trading using the same framework. In option trading, the role of an agent is played by an algo trading robot or a human option trader. The agent observes a market price ST and makes a trade or action AT. If we consider an agent that has already sold or bought an option, then by action AT we mean trading in the underlying stock. Clearly, the task of agent in this case involves planning and forecasting into the future. There are also feedback effects in option markets and stock markets. For example, delta hedging activities of large option holders can potentially and partially move the market. We will talk more about this later in this lesson. In addition to feedback effects, there are other market imperfection effects, such as transaction costs, holding costs, and liquidity effects. Now, the standard approach of mathematical finance tremendously simplifies this whole task, albeit at a substantial cost. Here, by the standard approach, I mean the so-called risk-neutral pricing methods that can be viewed as straightforward modifications of the Black-Scholes model that consider volatility non-constant or stochastic. If you have to optimally hedge an existing option position, then in this approach, planning amounts to sticking to the delta hedging strategy, and the forecasting task amounts to forecasting the stock volatility or implying it from market prices. Feedback effects from trading in options or in option underlying are neglected. Therefore, there is no backward feedback loop in this setting. Other market imperfections, such as transaction costs or limited stock liquidity, are also neglected. Option pricing and hedging in such models amount to solving partial differential equations, or PDEs, that describe option prices and generalize the Black-Scholes PDE. Now, in a previous course, we discussed how this setting can be modified to make it amenable to reinforcement learning. And it turns out that a key step to abandon is to abandon the continuous time formulation and go back to a discrete time formulation. It is very natural to consider time steps that correspond to actual rehedging frequencies for an option. If we rehedge daily, we should use daily time steps and so on. And the fact that we retain time steps finite make perfect hedging impossible, and this step is crucial. After this step is made, all other improvements can be added incrementally. Now, what would be such improvements? Well, beyond using discrete time steps and relying on Q-learning instead of a log-normal model, as in the Black-Scholes model, or any other model for that sake, we kept all other assumptions of the Black-Scholes model intact in this setting. And in particular, we neglected transaction costs in our model specification in the previous course. Under certain market conditions, this is a reasonable assumption, which is the same as in the original Black-Scholes model. And from the point of view of modeling, this produces a big simplification. And the reason is that without transaction costs, our system has no memory of past states. If trading in the stock is costless, we do not have to know how many stocks we held in the previous time step in order to optimally hedge at the current time step. We can view each optimal hedge as equivalent to assuming that we buy a full amount of the stock that is needed for the optimal hedge every time anew. And because stock trading is assumed to be costless, holding n stocks with market price ST is completely equivalent to holding the amount n times ST of cash. Now, from the perspective of reinforcement learning, it means that we do not have to keep the stock holding XT, in this case, as a part of the state vector. Therefore, in a simplified setting that we considered in the previous course, the state vector was made of only one number, ST, that is the stock price. Now, on the other hand, actions AT were actual values of the delta hedge. That is the amount of stock in the option replicating portfolio. And we also neglected feedback effects from trading in the underlying. Again, this is justified for a small option player the same way as in the Black-Scholes model, but it might be an inaccurate assumption for a big option player or in a liquid market. And this brings us to the topic of this lesson, where we will talk about modeling market imperfections for option pricing and hedging. In our next video, we will talk about the first item in this big topic, which is something called market liquidity.